Hello and welcome to a demo of my HoloLens 2 application for commissioning and controlling industrial ABB robots. The goal of my project is to leverage mixed reality to help clients and technicians commission machines for work in cells and set up all supervision processes for them. My project also allows users to remotely control both digital twins of robots and real machines using hand gestures. This functionality extends to creating path procedures for robots with a holographic twin of a real robot and then syncing the hologram's motion with that of the physical machine. There are two types of layouts that my application is designed for: a single robot working in a cell and multiple robots working together in an integrated work cell. I will only demo the first layout in this video. Users first need to pick what layout they will work with. All holograms in my app are anchored when stationary by using world locking. Without anchoring, holograms tend to drift and flicker even in distances closer than 3 meters, and especially beyond that. World locking takes the features of our physical environment, meaning surfaces, landmark objects, aka visually distinct objects, and creates a coordinate system that, unlike Unity's default one, anchors holograms to our actual real world. When moving, holograms are not anchored and instead retain their stability through space pins, or a grid of coordinates that gives accurate distances to the HoloLens when holograms move through the real world. Upon summoning a hologram, it is bound to the raycast or directional ray coming from our dominant hand until we pinch or otherwise attempt to interact with the handle that our raycast is pointing at. Then the hologram stops following our hand cursor and we can further manipulate it. UI panels in my app can also be billboarded. If that function is selected by tapping the I button above the panel, that panel will orient itself to always face the users. Hologram buttons will glow and make a sound when hovered to indicate a successful selection. Visual and audio feedback is incredibly important when designing mixed reality interfaces, since it's very easy for users unaccustomed with the HoloLens to lose track of their hand ray or become confused when they attempt an interaction that they thought should be successful. Users first need to select the machine model they would like to put in their physical environment as a holographic digital twin. In my demo, the only available machine is the IRB 120, so let's pick that one and pin it on our kitchen table. The primary way to control our robot is with an axis slider. This slider covers all types of ranges that can be configured for safe move supervision. Its range will adapt to the parameters we add to safe move, and it gives us a very intuitive and accurate way to jog the machine to whatever joint configuration we like. Speaking of parameters, we can configure global and zone data for all 6 SafeMove supervision functions through a panel that contains tables for each function. Parameters can be selected and then edited. The default keyboard for the HoloLens is really unsuited for typing lots of data comfortably, and so I made my own keyboard that contains only the keys we need. Once we've configured our safe axis range, we can test it out using the axis slider. If we set the joint's range to its axis position supervision range, the slider will go from one end of the limit to the other for the respective joint. We can also invert the limits, meaning that instead of one allowed range, we get 2 ranges adjacent to the factory limit range for each joint. In this case, we select the lower or upper inverted limit in our slider to iterate only over one of the 2 ranges. Tool orientation supervision limits the range at which the tool can rotate when it's at a certain vector. We visualize this with a cone that projects from the tool, and by changing the tolerance of the range, or the degrees that the tool is allowed to rotate, we expand or shrink the cone respectively. Axis speed supervision limits the minimum and maximum speed of each joint. When visualized and enabled, we see it as yellow concentrical circles wrapped around RPM or velocity gauges for each joint. We can also see a braking estimation for the first 3 joints. This is how many degrees those joints would travel in their current direction before the robot comes to a complete stop. When we edit axis speed parameters, we modify the yellow circles so they indicate the allowed speed range for that particular gauge. Any joint moving with speed supervision on must maintain a speed that fits in between the yellow arcs and doesn't stay behind it or pass it. Standstill supervision works while the robot is not moving but its motors are still running. Joints can be allowed to move within specific ranges in either direction. This is called tolerance. We can input tolerance in our table and see it visualized as green arcs on our joints. Then we can use our axis slider to iterate over those standstill ranges. When we release the slider, the tolerance range centers around the axis again, and we can iterate over that new position by refreshing our slider. When we configure SafeMove supervision, we do it either globally regardless of the robot's position, or we set up supervision for specific areas in the real world called safe zones. These are invisible polygonal volumes that trigger restrictions when the machine enters them. We can create them as holograms by first selecting how many sides we want our safe zone to have. Then we tap in the air at the location where we want the center of our zone to be. Safe zones have several groups of visuals and interactable handles that can be individually enabled or disabled. In addition to the 3D polygon, we can also see a 2D projection of the zone on the floor to help with spatial awareness of where exactly the zone is hovering. Zones can be moved and reshaped with hand gestures. We can also add new edges or remove existing ones. The green circle inside the zone's center signals collision with the robot. When the robot enters a zone, the SafeMove supervision parameters for that zone apply to the machine until it leaves it. When we reshape a zone, we are constantly updating its collision information. This means we can drag a zone's edge exactly to the point where it would collide with the robot in its current orientation. The visual components of each zone can be individually toggled depending on the use case scenario. We can enable and disable the coordinates of each edge. We can remove the walls, the connecting lines, the projection on the floor, and the handles we use to modify a zone. We can also enable move handles, which allow us to move a zone more precisely along a single axis. Finally, we can deactivate zones and leave their center as the only visual component. Here's an example of the robot passing through zones with different parameters for safe access range. We can see the data is immediately visualized on the machine as soon as a collision happens, or as soon as the robot leaves a zone. This lets us simulate real scenarios immediately without relying on input signals and without the need for physical props to visualize where zones are in the real world. ABB robots can be manually controlled via a remote control called Flex Pendant. It has a joystick that can be used to jog the robot in certain directions. We can emulate this functionality in our app by configuring how far each joint should move after an emulated joystick command and then pressing or holding these switches. We can move the robot more naturally by dragging it by the tip of its tool with hand gestures. You can see in the background that the digital twin robot in our Connected Robot Studio station is moving together with our hologram. We can either receive motion from Robot Studio and visualize it in our app, or we can pass motion data to Robot Studio by interacting with our robot hologram. But we can't do both at the same time because then the robot logically wouldn't move. We can also use our axis slider to further tweak the orientation of specific joints after we have settled on the tooltip's position. When we do this, all the joints will twist to a certain extent to reach the target position we want. If we don't want this to happen and we want to make very small tweaks to the robot's orientation, we can lock joints in place. This means that they will not move while we move unlocked joints. When we're happy with the robot's position, we can teach it an instruction. This represents one dot in our robot path that the robot must pass through, and when it gets there, all of its joints have to be in the same orientation that they were when we taught the instruction. We visualize the sequence of instructions with a faint red line. What we're creating now is a procedure for a machine. This is obviously a demonstration, so the path is not realistic, but we can imagine that this is, for example, a welding or an assembly line procedure that was created with just hand gestures and visualized in our real physical space. The three lines of text above our instruction button concern the actual pathing of the robot in Robot Studio between two instructions. We can tap on the arrow buttons to shift the parameter once, or we can hold an arrow to scroll through parameters quickly. Once we're done with our procedure, we stop passing data to Robot Studio and instead start receiving data so we can visualize our path. I intentionally use the very low speed parameters so we can see up close and in better detail how our procedure turned out. We toggle the blue line that's being left by the tool as it's moving along instructions. We can see the difference in our connecting red lines, which are all straight, and the actual pathing of the machine, which tends to curve around instructions. The blue line is our final procedure and is what a robot will follow in real life if we now connect a physical machine and use the procedure we made in our Robot Studio station. Procedures can be lightning quick, and it's hard to analyze them visually if we only have a few seconds to observe them happening with the HoloLens. This is where we can use our forward slider, which lets us record and replay robot motion. I'm going to start the same procedure again, but this time I will record it, and when it's over I will replay it. Now we can use our slider to get full control over the robot's speed and position along its path. We can rewind and fast forward at will. We can stop the motion or release the slider and let the motion continue naturally from the point to which we rewind it. So far we've only been using hand gestures to interact with our environment, and that can be fatiguing or outright impossible in some circumstances. We have in our toolbox a digital assistant called Louise. Louise can help us learn how to use the app through giving us tutorials and information about the things we interact with. She can also listen to us and do tasks in our environment. Let's start with her first mode, Focus Assist. When we hover over an interactable hologram, Louise will tell us what the hologram is used for. This works for every button and handle in our environment. Louise can also help us create comments and place them in our environment. I am recording an example comment to show how we can make comments using our digital assistant. We can leave notes or instructions for colleagues and put them contextually in our workspace. This feature also helps a lot with group work and communicating with clients on site. Thanks to spatial anchors, which are cloud-stored anchors for our holograms, we can place holographic comments in specific places in, let's say, a factory, and when a client walks through the factory the next day, they'll be able to see our comments where we left them. Louise is named after a Microsoft Cloud service for natural language parsing. It allows us to parse normal human speech for intent, objects, subjects, and sentence structure, and turn non-memorized commands into practical voice commands. I'll show you 3 examples of Louise assisting me by listening to me. Note that I could have said many variations of those sentences, and the command would still have been properly understood. Change the global upper limit of the first joint to 120 degrees and the lower limit to the negative equivalent. Rotate the third joint to 70 degrees. Help me create a safe zone with 25 edges. The last thing I will demonstrate is a safety check of our environment. We can enable a collider for ourselves and try to trigger a category stop by walking into a safe zone while the robot is moving. We should see the robot stop moving as soon as we enter the zone. This lets us simulate real physical safety scenarios completely digitally. This is the end of my demo. I want to thank Roman Parak for his help with networking code and advice for this project, as well as my friend Justin for his help with sound effects. Thank you very much for your time.